So with that said, I'm super happy to welcome LPL and steward Professor Daniel Apai, to kick off our. I have the intro on my phone. Which I put in my pocket. So Daniel, as I said, holds the position of a joint professor of astronomy and planetary science at Steward and LPL. Since 2022, he's also been serving as initially the interim and now the official Associate Dean for Research in the College of Science, supporting 14 departments, more than 400 faculty members, with an annual research expenditure of $180 million in the College of Science. So it's always worth remembering the College of Science is really a big and impressive enterprise, which Daniel is now helping us with. He earned his PhD in astrophysics from Heidelberg University and joined University of Arizona in 2011. Among his many activities, from brown dwarfs to exoplanet atmospheres, he also leads the NASA-funded Alien Earths astrobiology project that focuses on understanding the formation and habitability of nearby planetary systems. He's also developing a mission concept for a space telescope constellation and co-leading a supporting technology development program. And Daniel has published over 200 papers. I did an ADS search and discovered more than I would have guessed. We've published 28 papers together. So it's been a long and very productive collaboration. So with no further ado, I'll hand you over to Daniel.
Thank you, Mark, and thank you all for coming. I think this is going to be real fun to get feedback on some of the ideas that I wanted to share with you. This talk, in a sense, has two goals. In part, I would like to introduce those of you who haven't really been following our Alien Earth project. Alien Earth is a large NASA-funded astrobiology project, and I wanted to share with you what we have been working on over the past really decade. And also explore a little bit the future of exoplanet science. And in particular, I want to offer a path towards mapping out what are the big science questions in the field of exoplanets. And I want to explain to you that this is actually pretty important that we think about what are the questions that we want to answer in 20 years from now. And of course, this is a work that is really a result of an excellent collaboration. I enjoy working with many of the people, all of the people listed here, and many more in the Alien Earth team. So I will identify some of the first authors as we go through. So I wanted to start with Alien Earth. So Alien Earth is, as I mentioned, is a NASA-funded astrobiology project that we had been fortunate enough to lead here at the University of Arizona. And what I wanted to point out is, I think many of you in the field are aware of results coming out, the continuous stream of results coming out from this project. But in addition to the research results and highly cited papers, there is an underlying coordinated effort to support exoplanet missions and shape their future. So what is Alien Earth and its first part, EOS? So we are funded by the NASA ICAR program. This is the Interdisciplinary Consortium for Astrobiology Research. In the first 5-6 years, our team was called EOS, and the project was called EOS, Earth and Other Solar Systems. Then that ended, and we were fortunate enough that our second proposal was also selected. That was not a direct continuation, it was an indirect continuation with a different science focus, but much of the team was the same. That one is called Alien Earth. I will just refer as Alien Earth to both of these programs. Together, the two programs provided us $12 million in direct funding, and really it attracted many more other grants. We have supported over 40 researchers from these grants, including about 25 graduate students and postdocs. Probably the real number is higher. We have attracted a lot of additional funding, and including an entire space mission that is based on this research that we have done here. So I think by any metrics, this has been very successful, and for us, being part of it has been thrilling. The key question, if I were to boil down what Alien Earth is doing, the key question we are exploring is which nearby planetary systems are likely to harbor habitable planets and life. So it's a simple question that is very difficult to answer. So we have a very comprehensive framework to explore different aspects of this. If I wanted to give you the secret sauce for getting $12 million out of NASA, this would be it. And sorry for those who don't see it. It's the bottom of the slide. But what we do basically, I think all our competitors, those who have been on the top of the competition, have been excellent. So they all have done excellent science. Most of these competing programs have also been combining theory with observations. Many of them have done also experimental work like we did too. So we have done cutting edge research. You built on the real traditional strengths of Steward and LPL here. We were in a very strong position. I think what really made a difference for us is that we went beyond answering questions and doing fundamental research. We really connected our outputs or results to NASA missions. And so this is, in much of the talk, I will show you how we do that and how that is changing exoplanet missions and also ground-based instrumentations, and I think also the future of exoplanet science. So this is an overview. This was the cover of the proposal. You see the simple question identified there. I will not go through the whole project, but I just wanted to show you, of course, we had an excellent set of collaborators. Many of them are at the University of Arizona or were previously here or close collaborators. We have basically divided our work into 4 modules. The first module is exploring the conditions and timeline for planet formation. The second module is exploring the impact of planet formation pathways on planet composition. And so you build your planetary system, what the planets will be made of. The third module is exploring habitability and threats. And the fourth one is combining this information from the 3 modules and to inform exoplanet missions. So all of this is designed in a way that each of these projects is doing cutting edge research on its own, but they are of course coordinated closely and there's an information flow through the project. Today I will be mostly speaking about the last module where we connect to exoplanet missions. It's not possible to cover everything, in part because we are tracking the papers we have published. As of today, we have published more than 220 refereed papers from this project. So it's really impressive. It's akin to a major mission. These have been cited over 9,000 times, and the citation rate continues to increase. So it will be soon several thousand citations, 2,000-3,000 citations this year probably, and continues to include. So what I think the point here that I would like to make with these numbers is that in addition to the number of papers, we have made a very significant impact on the field. There is a whole number of papers that emerge that have 1 or several hundred citations. I listed a couple of the papers. Altogether, these, I think, arguably have impacted the field and changed the direction of the exoplanet field. At least one of these studies sparked a now accepted NASA mission that is following up on discoveries made here. So, and I could give several talks about the fundamental research that came out of these projects, and many of you in the room who are part of the team have been giving talks. But what today I wanted to emphasize in particular is how this project is linked to the big picture future of exoplanet science, exoplanet missions, and how we can use fundamental research to shape missions and ensure also that we are taking part and participating in those missions. So in addition to the basically fundamental research we have been carrying out, we have been developing modeling frameworks that allow us to provide critical information for missions. I will not go through all of these. I just wanted to highlight a couple. Today, I will be talking about Bioverse. So I will explain what this does. This is a mission, survey, and science definition framework. We have developed, this is in large part with Ilaria Pascucci, Hai Smulders, Fred Chesla, the Genesis database, and EPOS. These are tools that allow statistical comparisons of planet formation models to exoplanet demographics, which is now a booming field. When we started within EOS, we wrote some of the first papers in these comparisons, and we developed the first EPOS, the first forward modeling framework to compare statistically the exoplanet demographics. We are currently revising a paper on quantitative habitability. You will all know that Habitable Worlds Observatory is the flagship that NASA is going forward. We are building this flagship, designing and then building this flagship. In HW stands for habitable. But if we can be hard pressed to really quantify which of our targets is more likely to be habitable than another. We don't have a proper framework for that. So I led a science working group together with Rory Barnes, who also used to be here in LPL, within the NASA Nexus framework, a collaboration of about 40 people with input from over 100 scientists from multiple disciplines to help define a framework that allows us to quantify potential habitats in the solar system and in extrasolar planets. Today, I will not speaking about that either. I will just mention maybe these ones quickly in passing. Ben Rackham, who was a graduate student in the University of Arizona Stewart Observatory, working with me and Marjan Papa, who is somewhere here. We published a highly influential paper where we predicted that James Webb's observations of small transiting exoplanets will actually be limited by the stellar noise, which was previously not appreciated fully, and that turned out to be the case. So this is now seen as one of the major problems in the field, and that's sparked a team at Goddard Space Flight Center to propose a standalone dedicated telescope to study that effect. That's Pandora. Ben and I are playing important roles in that mission. Dynamite is another tool in this toolkit. Dynamite was developed by Jamie Dietrich. She's sitting in the back, who worked with me. There we set out to develop a framework in which we can probabilistically predict where are missing planets in exoplanetary systems. That's important because in most systems, we are missing the vast majority of the planet. And it turns out, thanks to Jamie's work, that we can actually, with very high confidence, predict missing planets in a typical system. And then Ilaria's team has been doing cutting-edge work on planet demographics, occurrence rates, which is very important if you want to figure out what your mission will be able to detect. So this was just, I know it's a little bit dry programmatic, but I wanted to make some of these connections. Let me switch now a little bit and then talk about exoplanets. Where are we in the field of exoplanets? And then how can we go about designing really big projects in this field, which is more tricky than it sounds. So this, I just pulled this from ADS about half a year ago or so. This shows the number of refereed papers that are exoplanet related, and certainly there's a bit of a noise in this, but this is probably pretty representative of the trend. What we see here is, of course, for a long time there were not many papers. It was not the best field to work at. But then, starting from 1995, as we figured out how to detect planets, this field took off. Now, what is interesting is that it didn't converge to a number. It is still growing fast. And so this is over 5,000 papers. Probably if I do it today, it would be closer to 6,000 papers per year. So how many people are working in this field? So if you take, yes, thank you. I was actually thinking in the community. So if you say on average, one person publishes one paper, which is not great, but you could argue that the field basically in 20 years or so probably increased by an order of magnitude, or maybe a factor of 20 or 30 in population. So it keeps on increasing because it's a cool field. People join the field. We have thousands of brains that we can engage to solve big problems. One of the next questions is how more can this grow? Now we are starting to be actually, the exoplanet starts to be the largest community within astronomy. It is now in the James Webb time allocation. From the statistics I've seen, that's the largest number of hours actually went to the field of exoplanets, which is very different from how Hubble used to operate. So lots of people are moving in. It's an exciting field. So are we living in the golden age of exoplanets? Let me show you another animation. Hopefully this will work. Okay, it does. So this is number of exoplanets detected, and you have seen some versions of this, but this one will be a bit different. So you can see that initially we almost knew no planets, and then we started to detect more and more planets. And you could think we are now living in the golden age of exoplanet exploration, where we basically have reached and exceeded 5,000 exoplanets. But if you look in the next 20 years, we are nowhere, right? So with the missions that are coming up, we will be talking about hundreds of thousands of exoplanets. Most of these are candidates. Not all of them are confirmed, but statistically speaking, they are useful data sets. And I would say that this is an underestimate. It only includes missions that are being built. There are several other missions that people are working on that could multiply this number. Okay, so we could easily reach 500,000 exoplanet candidates in the next 20 years. That's pretty amazing. Does it mean that we now know 200,000 times more than we did in 2010? So, and we can ask, it's worth asking, what fuels this growth, right? Did we just become suddenly much smarter so that now we can detect so many planets, while before we couldn't detect these planets? So I would argue that what's behind here is not just smart people, but maybe even more importantly, Moore's law. That may be a bit disappointing, but let me explain why. What I think you see there is that we have transitioned, we managed to parallelize our exoplanet discovery methods. Almost everything that you see there in discoveries is coming from a parallel search, where you are covering large fields in time domain astrophysics. You are looking for transits, you are looking for gravitational lenses, or you are looking over a very large field for motions of the stars measured at high precision. What you need to do this is the ability to basically process large amounts of data, make measurements at very high precision. It's not just ideas, but very much technology that's behind it. So this is important, and Moore's law will continues to impact many other aspects of our field. I listed a couple of those there, and in another talk, I go more into details in those, but here I wanted to really focus on exoplanets. So what I think there are a couple of other interesting points. The planet discovery has really basically shifted to space telescopes. Ground-based telescopes have far fewer contributions in the future. Some of them will be still very interesting, so they have a role, but almost everything that you see here is coming from actually relatively small space telescopes. There is a vast number of planets, but most of these planets we will know almost nothing of. And I will touch on that soon. So the relevance of ground-based telescopes is fading. It is just in terms of the discovery rate, the statistics, it's all coming from space. I would argue that extremely large telescopes will still be important because they will be providing basically the lens, the magnifying lens, through which we can study a few particularly interesting planets, but not the hundreds of thousands of candidates that we are discovering. So let me switch a little bit and talk about information value and complexity. So what I think we have seen first when we entered the field, we started to find really interesting planets. Every planet was unique. We found the first hot Jupiter, the first sub-Neptune. They were all super exciting. Now we find many more planets. Many of them are similar, but we are pushing the boundaries towards cooler and cooler and smaller planets. What happens is that when you move away from the extremes like a hot Jupiter, I would argue that, and towards something closer to Earth, I would argue that the complexity of the system is going to increase rapidly. It's just like a star can be characterized with far fewer parameters than you need to characterize, say, a hot Jupiter. But then if you move to an Earth-like planet, you really speak about systems of systems, complex chemistry, physics, feedback cycles, perhaps even biology coupled to it. So I think on one hand, we are getting more and more planets, but most of those have information contents that's actually converging to zero. At the same time, we are pushing into a field where we need more and more information to better understand these planets. So it's pretty exciting. We do have advantages. We have lots of data still coming in as an aggregate, and we have these many thousands of people who are thinking in the field how to use that data. But I think we need to think about, and we need to realize that this is what I call a cliff of complexity. As we enter to low temperature atmospheres, planets that are increasingly similar to Earth, we are dealing with a very complex problem, and we need data, and not just data, but actually information and knowledge. So this is, I think, it's a point that is obvious to many of you, but for many of you may not be. So in the beginning of the exoplanet field, every measurement was new. Every data point was a Nature paper. I still remember. We knew all the 3 exoplanets by name that were known at that point. Whatever you could measure was amazing. We passed that, fortunately. We now know so much more that most measurements don't actually provide much information. So it is important to distinguish between data, which is, you could refer to it as a result of the measurements, information, which is basically data that is maybe unexpected, something that you could not have predicted. And I would say knowledge is the ability that you are able to explain what you are seeing and correctly predict future observations. These are different layers, right? And I think in the field, we often make a mistake of thinking that if I collect more data, that will translate to knowledge. But increasingly, it won't, because we already have a lot of data. So, which brings me to inflation, hyperinflation. So, and just to make a point here, right? In 1995, when the first hot Jupiter was discovered, that radio velocity measurement, which is today completely standard, yielded a Nobel Prize shared between Kellos and Mayor. So now today, if you are a PhD student and you discover a hot Jupiter, you will not get a PhD for that alone. That's probably just not even enough, right? In fact, today, hot Jupiter discovery would probably be buried in the literature of maybe about 20,000 publications. So if you want just for some fun, if you can calculate this, what would be the sustained inflation rate? And of course, this is, you could get with a different number with different assumptions, but I would say maybe about 30%. So basically the data that we take is rapidly eroding in value because so many other people are doing similar measurements. Now, 1 year to the next is not such a big deal, but if you took data 10 years ago, that's probably not worth publishing anymore. Now, this is a challenge because we are building large projects that take 20 to 30 years to build. How can we ensure that the telescopes that we will fly 20 years from now are answering the questions that will be important then? So that's really basically the kind of the motivation behind the work that we are doing. And so I came to this kind of a long way. I have worked and led several NASA and larger committees that looked at the science questions that are underpinning big missions. So I was part of the ExoPAG executive committee and felt, and many other people did too, that so much, this was 2015, 2016, so much of the discussion about future mission was driven by very simplistic scientific questions that we felt that it is important that there is a document, a report that explores what are the actual questions we want to measure, not just detecting oxygen, what are the questions we want to answer. So I led a report that was published in 2017. It's a 100-page report where we are asking the questions, and many in the community contributed to what are the, say you have an ability to detect Earth-sized planets or planets that are, we address different types of planets. What are the questions you would want to answer after that? What comes next? So I think that helped. Some of the reports that came later, STDT work too. Then I was asked to, by the Space Telescope Science Institute's director, before TESS was launched, before James Webb was launched, to pull together a committee and try to think how we could maximize the science output of Hubble, James Webb, and TESS. So this was super exciting. We managed to deliver a report in 9 months, and we did a modeling of information flow and target flow between these missions to point out where are the bottlenecks in the system. And thanks to that, the Hubble science program was changed to enlarge the bottleneck so that we are more able to exploit the synergy. Then I also served for 4 years on the GMT Science Advisory Committee, where I helped with the Exoplanet science case. And in all of these, one thing that I wished we could have done, but it was never really possible, was to answer the question, what is the sample size? What is the sample size that we need to answer certain questions? How many planets should be detecting and studying? So if you look at the Habitable Worlds Observatory recommendation from the Astro 2020 Decadal Survey, the recommendation is to have a sample of about 25. But that number, I mean, it sounds very reasonable, it's probably a very good number, but to actually figure out that you need 25 and 19 is not enough, 5 is not enough, or 75 is not needed, that's much more difficult. that's where actually you have to face the question that we have to really understand what these telescopes are going to do and what we want them to do, because once we build them, we cannot go back and just change parameters. So I proposed as part of our proposal to the NASA astrobiology program to develop a framework that allows us to test exoplanet missions, exoplanet surveys, not just by the number of planets that they can detect, but the science questions that they can statistically answer. So that is Bioverse. So Bioverse was a project that started Alex Bixel, who worked in my group. He was a PhD student, did an amazing work, developed the first version of Bioverse, which we published in 2021. He did receive a PhD at the end. It all went well for Alex, and he moved on to SpaceX. So now he's launching large numbers of satellites into space. That was his goal. And then Bioverse was then continued by Kevin Hardegger-Ullman, who is in the audience. He has done, together with Martin Schlecker, an amazing work of taking this framework to the next level, expanding it, and then using it for different questions. So I will show you a couple of examples, and then I will go relatively quickly, and I'm happy to take questions about some of the technical details if you have at the end. So basically what the premise here was that the number of planets that are detectable in a mission does not equal the science yield, the knowledge gained, right? So instead, we argued that we should follow the scientific method. That's one good way of doing it, and say, what hypothesis can I test with this data set? And then I can say, okay, I want a statistical test, and then I can determine what is the sample size I need, what is the signal to noise I need. So this is fairly standard if you are talking about a smaller proposal, right? I think a proposal to Hubble or James Webb, that's pretty much a standard. But when you're talking about big projects, that's much more difficult to do because it takes years of investment of developing a really complex modular framework. So that's what we did here. We created many modules, and that we are supporting a large number of mission concepts, missions, and science cases. So I will just point out these 3 papers that you can find more details. There will be others that show different applications, but if you want to cite Bioverse, these are the 3 papers to cite. So what does Bioverse do? So basically, let me see if, okay. Basically on the left-hand side, what you see is that we create planetary systems. So we take host stars. These host stars are actually drawn from Gaia. So this was work of Kevin. He characterized and integrated all the Gaia stars and then filtered them and characterized them further within about 130 parsecs so that we can create basically a target sample for pretty much any exoplanet survey that you may wish, whether it's direct imaging, transits, interferometry, etc. And so around each of these actual stars with their actual properties, we create planetary systems. Those planetary systems are fully consistent with the state-of-the-art knowledge of exoplanet planetary systems. And then we can classify the planets or set their properties as we wish. And we can apply population level trends. I will show you examples, but we can, for example, make the planets in the habitable zone have a different color, or more likely to have water, or more likely to have oxygen. Those are the kind of things that we can test. We have in the middle column, we have a survey description. We can execute surveys, simulate the execution of surveys with large ground-based and space-based telescopes, even small space-based telescopes. And then we can see which planets you detect, what are the properties that you can measure given the simulated sample. And then ultimately, we can see in these simulated results whether or not we were able to statistically test the hypothesis that we set out with. For example, planets in the habitable zone have different properties. We execute the simulations in a Monte Carlo fashion hundreds of times, and then we can see in what fraction of the time we got a conclusive statistical answer. So this is pretty powerful, and this is the first time that such a framework has been developed for exoplanet missions. This is something that basically the different study groups usually didn't have resources and time to do. So what are the key uses for Bioverse? It can inform and guide exoplanet surveys and mission science definition, and it can support trade studies. You can ask the question, and we did, what happens if I decrease the size of my telescope? I change the wavelength range of my observations. Can I still answer that question, or could I answer a different question? So, and you can do this in a uniform manner. So if you have multiple teams bringing their own mission concepts or survey ideas, you no longer have apples to oranges comparison. You have a uniform basis where you can compare them. I think it's important that it's not only relevant for missions, but it's also important for modeling, because it's very easy to create a highly complex model. But if you're a modeler and you want to make sure that your models eventually get tested, you know whether right or wrong, they have to be observational testable at some point. So I like this quote that all models are wrong, but some are useful. Which are the useful models? The useful models are the one that, in most cases, that will be eventually testable in the near future. So, and with this toolkit, we can do multi-mission synergy studies. So what happens if we combine knowledge from Roman with knowledge that we may gain from Habitable Earth Observatory or GMT? What will be the combined knowledge? How can these missions really inform each other? So these are important questions in programmatics, and they drive tens or hundreds of millions dollar worth questions. So I will probably just skim this a little bit. It's a highly modular framework, and if you love programs and you want to work with this, we are very happy to speak with you. Many groups have actually engaged with us, and multiple papers are now in publication. We have 5 papers published and 5 that are in progress and under review, and an increasing number of teams are reaching out for us to use it. So let me show you some fun examples of what are the questions that I think that we studied and that we could, with the right telescope architecture, study. And I like these. I think this is fun because I'm excited about detecting oxygen, but what I'm really interested in is what are the actual science questions that we can understand, whether or not there is life. I want to understand those planets, the planetary processes, how they form. I'm more interested in that than just detecting oxygen or potential signatures of life. So we enjoyed asking these projects. So one of the first questions we started is that it's a very simple hypothesis. Could we test this simple hypothesis? Are Earth-sized planets in the habitable zone more likely to have water vapor? So very simple question. What we did is that we had an assumption that, and it includes false positives, it includes non-Earth-like planets and different complications we put there to make it more realistic. But generally, we said if a planet we simulated these planetary systems, and it has a higher likelihood to have water vapor in the atmosphere if it's in the habitable zone. And you can vary by how much, how many planets you have, what is your survey. We ran it through Bioverse. This was one of the first examples on which we demonstrated it. And you see 2 panels here, lots of information. I will not go through everything. We don't have to understand all the details, but this one shows, and you see a little logo there showing a directly imaged planet, and then below habitable zone question. So this is one of the tests that we did to explore whether or not the habitable zone concept as a whole, could it be testable? So, and we varied here, for example, the fraction of exo-Earths that have water vapor, and a fraction of non-habitable planets that have water vapor. And so you can explore what is the statistical power. The darker green it is, the more likely is that your mission, in this case, this was a 50-meter direct imaging mission, a LUAR-A, could answer the test your hypothesis. On the right-hand side, you see a similar experiment done on a transiting planet mission, where there would be a very large light collecting area. And then you can tweak this, you can, most importantly, support trade studies. So this was the first simple hypothesis. Then one thing I would love to answer once we start to get this data is this question: is Earth's atmospheric evolution typical? Is what happened to Earth, should we expect that a fair fraction of other planets actually undergo this atmospheric evolution? And really, I mean, really here, big picture, with Earth, basically, roughly in the first half of Earth's history, there was not much free oxygen in the atmosphere. The concentrations were extremely low. We have very tight upper limits. And then there was a great oxidation event, and there was more complexity to it. But basically, in the second half of Earth's evolution, free oxygen was abundant in the atmosphere. And that transformed many things on Earth. So we created a model where we could vary whether every planet simplest hypothesis that every planet is an Earth twin. We also allowed planets to have an oxygenation timescale. A typical timescale could be short. Maybe Earth was maybe a typical planet, or maybe it was an atypical planet. Maybe on most planets, it takes much longer to have that transition. So we built a simple model for that, and we could explore the detectability and testability of this hypothesis. And in doing so, we also actually predicted, which is, I think in retrospect, a relatively simple prediction, but I think it is important, is that there should be an age-oxygen content correlation, positive correlation among exoers, if oxygen is typically a result of biological activity. On Earth, it took a while for oxygen to develop because oxygen photosynthesis is so complex, and then probably led also to the change of the redox state of the planet. So if it had happened if we find planets where it happens in less than 10 million years or 20 million years, I would be suspicious of that not being the result of biological activity. So these are things you can test just by adding, for example, age information to your system and designing your sample in a way that you can do age comparisons when the mission allows that. So we did find that in a fair fraction of the parameter space with this is the gray, upper right gray, this correlation could be testable. And that basically demonstrates the point. I can come back to this if there's more question. We ran basically a LUR-A simulation. We did this Nautilus space mission concept, which I will, I talked about this, I think, 2 years ago. Here, it's a mission concept. We are working on technology development. That's a transiting mission with very large collecting area. And so we could explore the parameter space and identify which parts of the parameter space allow us to test this hypothesis. We also applied, and this is primarily the work of Kevin Hardegre-Ullman here, or Bioverse framework, to the very important question of what can we learn from O2 surveys of extremely large telescopes. So we are all very excited to see GMT, TMT, and the European Extremely Large Telescope come online in the next 5 to 10 years. And there's a real question, how are we going to best use those telescopes? What is that we can learn from it? What is that we cannot learn from? And so there were a series of papers starting from 2013 that created a lot of enthusiasm in the literature about the possibility that we could detect oxygen potentially in transiting exoplanets with these telescopes. So, okay, this may sound simple to do, but it is not. The key challenge is that we want to detect a molecule in an exoplanet by looking through our atmosphere that has the same molecule in it, right? So you have to basically be able to tell apart which oxygen molecule is in the terrestrial atmosphere and which oxygen molecule is around the Alpha Centauri, for example. And so the idea was that if you do high enough resolution spectroscopy, and this is a nice simulation from Kevin, and you use the fact that those planets will have a time-dependent relative velocity to Earth. Sometimes they come towards us, sometimes they move away from us, and the system velocity is different too. Then if things line up well, the terrestrial and the extraterrestrial oxygen lines will be misaligned in the wavelength space, and then you may be able to get a signal. If they are perfectly aligned, you will not see anything. And so this this assumption was used in multiple papers, and the conclusions has been that if you look at the right type of stars, then maybe in a few dozen transits, this is doable. So this is exciting. A transit maybe is only 4 hours long, 5 hours long, maybe with a baseline. So if you take a dozen transits, it's 60 hours. That sounds easy. Of course, these studies did not really, and they were exploratory studies, they did not consider fully the complexity. So our study, what we did is we simulated entire surveys that you would execute with this telescope. We actually considered real host stars rather than hypothetical host stars. We considered how frequently do you actually have a transiting planet of the right size with the right period. We actually track orbital radial velocity variations, and we considered the target visibility. Can I really observe this target? What's the probability? And then we consider multiple telescopes and also consider weather conditions. All of this is pretty well known, actually, statistically. it takes a lot of time and a lot of really high precision work to put this in, especially integrating all the Gaia work. So this is, again, I wanted to highlight Kevin's careful work on this. He folded in a lot of knowledge from Gaia and then other databases to calibrate stellar properties well, remove those that would not be good targets, characterize the radio velocity. And so that he could consider also which targets are observable when, which wavelengths, etc. What you see here in this figure is on the top row, you see the GMT, below the TMT, ELT, and then combined. These are basically targets on the left where the basic just counts the planets that are available. And as you go towards the right, different constraints are folded in. And you see basically the number of targets decreasing. And then the last column shows if you fold in the geometric transit probability. So the probability that these are actually transiting. And most of the planets disappear, of course, because most of them are not transiting. So the result of this was a much more realistic assessment of what we can expect that we will be finding. Kevin also looked at more optimistic and less optimistic situations, calculated signal to noise that can be built up. And I think this reveals the challenge of doing these observations. So this basically shows the number of planets where you can be able to probe Earth-like oxygen levels. And on the x-axis, you see the survey duration. And that is not measured in days, that is measured in years, in fact, centuries. So the fact is that this method, while conceptually attractive, if you fold in the complexities, it is a very low efficiency method. We considered also going large or combining all the ELTs, 3 of them together, or even building larger telescope, 50 meter or 75 or even 100 meter diameter ground-based telescope. There are some ways, ideas how to collect that much light. And it does get better, but you are still talking about extremely long integration times. Unfortunately, this model is still optimistic. We still didn't include proper systematic noise model of what it takes to combine signal over, say, a century from a telescope. We don't consider changes in the Earth's atmosphere. We assume it's static, but in reality it's not. And we also don't consider changes in the instrument, which also is, all of this is significant when you are looking for a 3 sigma detection over centuries. So this is, I would just say, we can do many great science with the GMT, TMT, ELT, but probably not this one. So it is an important question then to ask, what should we be focusing on? Kevin's next paper, which is on arXiv, they took the next step and look at direct imaging. What can we do with direct imaging? So in direct imaging, you have the advantage that you don't have to restrict your observations during the transit event. That means that you have many more opportunities in a given year, many more hours that you can make use of to collect photons. So that helps. Also, you don't have to restrict yourself to transiting geometries. That helps too. On the other hand, you do have to spatially resolve the star and the planet. And that means that you cannot look at faraway systems because then the projected separation of the habitable zone will be too small for your inner working angle. So combining all of these and then transitioning basically all the tools from the previous survey allowed Kevin and our team to assess what the GMT, for example, and the ELT could be doing in terms of probing down to Earth-like oxygen levels. And the numbers here look better. So basically, in a couple of years, both of these telescopes would allow us to probe, in the best case, I will mention that this is the best case, a handful of planets. So we can even start thinking about doing statistics. And so this is much more exciting. This does assume, though, that we basically push these systems to the theoretical, pretty much limits, that we reach basically photon noise limited signal to noise. That is currently not the case. The current observations are still a factor of 10 to 50 away from photon noise limited observations. So there's still ways to go figuring out how to calibrate systematics. But I think the potential is there. And we can, yes?
Sorry if I'm missing this, Daniel.
Yeah, go on.
I don't understand the difference between what you're showing here, which is something that's possible.
Yes.
Your previous slide, that's impossible.
Okay, so maybe I was going a bit too fast. So the previous slide basically was focusing on transits. And so we are restricted to planets that are transiting in front of the host star. And here we basically repeated and expanded that to allow direct imaging. So this is a direct imaging simulation. Thank you for probably going too fast. So direct imaging is much more promising, but we still have to work on making sure that we reach these results. I will just show another example quickly. This is, we also made a hypothesis based on outgassing models that planets that are just interior of the inner edge of the habitable zone because of a super runaway state may have inflated radii. This is based on models that Caroline Dorn and Tim Lichtenberg created. We asked the question if that hypothesis would be true. Could we test this with measurements of transiting planets? So this was work by Martin Schlecker, also postdoc in my group. And Martin has simulated this model predicted increase in the size of the planet at the inner edge of the habitable zone and varied the sample size. And the key result there is that you don't need direct imaging or high contrast imaging for this. Just by measuring the planets of sizes of transiting planets, if the sample size is large enough and you sample the right radii, you may be able to test this hypothesis. So we actually found that Plato, the European Transit Mission, has a potential. It may be able to do this if they plan the target follow-up correctly. So Martin visited the space agency there, DLR, and then we alerted them to this opportunity, and we continue to communicate with them on how to tweak Plato. We also have been working on integrating biology into Bioverse, and I know I still have 60 seconds, right? So I will keep that. So basically, we have been working with a group led by Regis Ferrier from our ecology and evolutionary biology, Stefan Mazevet from Nice Observatory, to integrate planetary scale ecosystems models that have been used for the early Earth, early Mars and Enceladus. We have integrated these into Bioverse so that we can ask questions if we have a large enough sample of planets that we detected and we can characterize them. Could we constrain planetary scale like metabolic activity, methanogens, oxygenic photosynthesis, for example? I will mention that we are also working with Noah Tucho and Chris Stark, who are working on the Habitable Worlds Observatory mission concept. We have been developing modules for Bioverse to be able to create predictions and support trait studies for the Habitable Worlds Observatory. So I think some of these missions may seem to be in the future, but we are at an important point in time. These are basically, we are at this time when we can make predictions and guide trait studies that help drive decisions that will determine what we will be able to do in the next 2 decades with these telescopes. If we make the wrong decisions here, it will be too late later to change them. So we think that this is high impact science through changing and shaping these missions. These are some of the questions we have already looked at. Some of the others we are still working on that will help strengthen the science cases for these and other missions. They also put us in a premier position to participate in these missions, bring new ideas, or propose new missions too. And these are the different teams we have been working with and continue to collaborate with them. So in summary, this is one large module within the Alien Earth team that I showed you. There's much more going on Alien Earth. I hope that you will find ways, if you haven't already, to engage with us. We have been in part developing cutting edge science, but also focusing on this aspect, connecting cutting edge science with mission concepts to shape the future of exoplanet science. Let me stop there and thank you for your attention.
Thank you. Thank you, Daniel, for a great overview of what you're working on. As I was sitting here, I mean, we heard the things that are really hard and some things that are maybe not too far in the future, like the runaway greenhouse. Is there processes we can think about testing sooner, like how common are volcanic gases in terrestrial atmospheres, or something that's maybe 3 or 4 years away and not 10 or more years away?
That's a great question. And the answer is yes, of course. So there multiple ways. So first of all, I think today I focus mostly on potentially habitable planets and Earth-like planets. There's so much science that we can do now with James Webb and then very soon with these telescopes on non-Earth-like planets. And I think, I really think that, this is the right department to appreciate that we should not be focusing on these missions as just Earth observers. We really need to think about the planetary science that we can learn with these. I think we need to understand things like cloud formation, cloud properties, and then we have to have a model that we can use when we can calibrate at higher temperatures, but then extrapolate those processes to lower temperatures. There's a lot of laboratory science that I think can be done. We benefit a lot, all of these studies benefit a lot from better understanding the planets, our own planet's interior, outgassing to evolution of Earth. We can fold in planet formation. I think some of the most interesting hypotheses that we will be able to test with these future missions could be really planet formation driven. I think we see planet formation and then planetary atmospheric evolution, including atmospheric losses, as a major shaper of the exoplanet demographics. And so I think pulling those in, pushing them to lower temperatures, better understanding them, they will be helpful. And I think currently James Webb is one of the most powerful tools. And then we have, of course, the ground-based telescopes. I think the large ground-based telescopes, ELTs, will provide a new source of information that will be exciting for a while.
Any questions?
So this is really impressive work to look at the parameter spaces and understand. It's very sensitive, but I want to ask this question sharply.
Mm-hmm.
So, we've ordered up LUVOIR, essentially, or Habitable World Observatory, and we want to look for life. Okay, so I order up, a catalog of exoplanets. I let other people discover those, and now I want to and look for life. With what you're doing, what you're testing, am I going to do the obvious thing in the end? I'm going to say, okay, fine, but really I'm just going to look for Earths and habitable zones around, early G-type stars, which is what we are. Or, is what you're doing, say, well, no, actually what you really want to do is look at a different parameter space, say K stars or, different size planets or different characteristics. If you're aiming for the simple thing of detecting life, what is it you actually are going to do with Habitable Worlds Observatory? How do you triage the list of exoplanets you get for this?
Okay, there's lots of great questions there. I will try to unpack it quickly. So one question is whether there will be ultimately easy to find life, and will we do the obvious? My opinion is that finding life is not going to be easy. And if we want to convince ourselves that we have a correct interpretation, we need statistics. I may be pessimistic, but I don't think that even if you would see a low resolution spectrum of Earth somewhere else, everybody would be convinced that that's life. And we have the examples from Mars, Venus, even the Moon, right? Where people for long times there were some people convinced that there is life on them. So I think if we learn anything, I think is that planets are complex and we need a large sample to understand what are the trends, the outliers, the clusters, and then know what are the processes that shape them. So that's my approach would be, I think if we want to be confident we understand how we interpret, we need a sample. This can help you figure out how large is the sample, depending on your hypothesis. I think a separate but related question is to ask, will Habitable Worlds Observatory be the right one to find life? If you ask me, not. I think that's not. And even if it would reach 25 planets, which I don't think it's going to be possible, ExoEarth candidates, I think the actual yield is going to be much lower than that. Man, can go there. But even if you find 25 and out of them, 3 of them are more similar to Earth, I would not feel confident to say that those are planets with life necessarily. Also because there is no ability to repeat the experiment, right? So I'm worried about I would not think that Habitable Worlds is.
Asking for it? Should we not be asking for it?
I think we should have. It's a longer discussion. I'm happy to have that discussion with you. I think if you trace, but we should have it separately, but yes, yeah.
Any more questions?
Yes, actually, this is a question a little bit adjacent to yours. So I was wondering if, e.g., I'm doing some research to try and figure out which systems are likely to have water and volatiles delivered in the habitable zone. How easy would it be to integrate that kind of conditions into the set of modules that you presented and that Martin Schlecker is working on, for instance?
That's a good, and thank you for bringing this up. This is generally, it takes effort to integrate these modules, but it's not a huge amount of effort. There are two things I would mention there. It's because of the limited information quantity that we will be able to gain from these missions. They will not constrain highly complex models. So what we are looking at is always the biggest knobs in the system. And then we generally look at, from a statistical standpoint, clusters, discontinuities, or strong trends. So if you have a model that says, okay, there is a very large, say, water abundance difference in the inner and outer planetary systems, and I have a hypothesis for that, we can see if it's testable or not. And it's entirely doable. It was a bit surprising to me, at the end, if you assess the information content that, we project will come, that we are still basically are able to test some of the simple hypotheses, but anything that is really more complex will need much more data for it. So finding the right simple model, that predicts a big difference in the observables, that's basically the way to go. And we certainly have like the radius valley is an example for something like that was predicted. It's a very observable effect. It's a really nice kind of statistical match.
One last question.
Daniel, you mentioned Pandora, which is a mission that's coming relatively soon, as something inspired by your previous work on some of the difficulties with certain sites. Could you describe Pandora a little bit?
Thank you, Ben. So Pandora is amazing. And it's also special, not only because it's coming, the science case is coming from here, but we actually will be operating a telescope from here. So in the Applied Research Building, that's the first mission that will be operated by the University of Arizona. We will be mission control for that. And we are launching a year from now. So it's pretty exciting. It's a small set in the NASA Pioneers mission. But small set, I was surprised. You can actually fit a 45 centimeter diameter telescope into a small set budget now, in part because it's reusing components. So that is going to do transit spectroscopy, low resolution near-infrared transit spectroscopy, similar to Hubble, but smaller aperture, and parallel near UV photometry. The goal of the mission is to understand stellar heterogeneity and how it impacts the observed transmission spectra of planets. So the work that we have done with Ben Rackham and Martin Papa, the finding there was that, I used to teach that if you have a transiting planet, right, you observe the system before the transit, during the transit, you divide the two, and the star, poof, cancels out. It doesn't, unfortunately. To a small level, it survives, and the smaller your planet, the bigger problem this is. And there is no real observational way to cancel it out. We have to understand the star, model it, so that we can assign uncertainties. And Hubble and James Webb cannot monitor stars, but with a small set you can. So we'll be monitoring the stars, rotate as they rotate, study them, revisit them 20 times, and build a comprehensive picture.
Well, on that note, I love this stuff. It's the intersection of Steward and LPL and planetary processes, and everything that we do together is really the future of this field. So thank you all for coming. Let's thank Daniel again.